All right, welcome back. So I'm actually going to now kind of really roll into graduate fluid mechanics. Now, if you look at a sort of standard undergraduate fluid mechanics book and you kind of look at what I've done so far, you're going to see me skip over a couple of things. One, rotating flows, like kind of turbo machinery, was super important. The undergraduate version, it's almost like this little taste and almost just defending if you have to come at it again. But every single time I've taught or seen taught, whether it's like a gas turbine class or pump class, you basically always come back and do that anyways. So I feel like it's double dipping here, and I will absolutely, I'm going to come back and talk about gas turbines on all these book clubs. And so we'll hit it there. The other one is open flows. And so, if you're a civil engineer and you're dealing with rivers or different kind of stuff, like, yes, there's some interesting things that then happen with open surface flows and waves and things like that. And I may come back later. I'm a naval officer. And so, yeah, all the kind of stuff with ships and things like that. I actually find it more useful on those open flows first to actually do it where, again, what you actually see on the graduate fluid mechanics, where we actually we'll talk about that first before kind of coming back to it. And so really at this point, we've kind of concluded what I wanted to get out of that undergraduate textbook. And so then really moving on to the graduate level, but I've been interspersing this all along. And so really, if you take a look at, for this class, Panton's a great book just because how complete it is. There are other graduate texts I've taught out of that are sort of less complete than Panton but smaller. But this is really such a great textbook. And so, if you look at the end of chapter 1, you should be able to go read it really well at this point. There's a great discussion on what does it mean to be the continuum, and honestly, the best graph I love about this is sort of, log of whether you want to think volume or distance. I'll do it as volume, and you have effectively all of this noise, whether you want to say it's quantum mechanical or at some point, there are gaps between molecules and all of this stuff. So at some point, if this is say like density, then density gets well defined for a little while, and then at some point it's not defined anymore. Why? Because if it's if you're talking about an ocean, at some point the ocean runs into continents, or if you're talking an ocean like this, it's actually really skinny and runs up top, or if this air at some point it's really high in the atmosphere, and so it's not so continuous, right? Eventually you get into orbit. So almost any system you talk about has clearly this limit of on size where we would say it's continuous, just based on work. Probably the largest number of this might be if you're looking at some like interplanetary dust that you're at some point treating as density, but that would sort of be it. So there's always a sort of the right hand that we understand. There are some flows where this will become important, where all of a sudden, you have to start taking into account rarefied gas, the fact that it's not quite continuous. So that's some interesting applications there for sure, especially in some interesting combinations like orbital reentry and things like that can hit some of that sort of rarefied gas thing. So that one's good. Chapter 2 is just a great review of thermo. So go read it again because Panton taught this at a sort of more graduate level, and he himself was a math, lived in applied math PhD. You're going to see, I think, one of the better handling of thermodynamics that I've done here, because I've sort of pulled stuff in from statistical mechanics and taught a little higher math level. So you'll see a good review there. And the important part, I guess I will say, so even though Panton's book title is Incompressible Flows, like at this point, he actually covers all sorts of things, including compressible flows. But really, if you take dH, and we've already talked about enthalpy, which is great. We know this is du plus p dv. And then remember that coefficient, constant pressure coefficient heat is dH. All right. T at constant pressure, that's a T, right? Which is the derivative with respect to temperature of E plus P over rho. We'll do it from that point of view. And then if it's incompressible, right, the pressure isn't changing the temperature, and density is not changing with temperature because none of them are. And so that's effectively the same as just dE dt, which is just the same as CV. And so you already have sort of this definition that the ratios is 1. So that's one way you can sort of treat incompressible flows. is that the ratio between specific heats is 1. You got to be careful. Some of the formulas that you may have seen might be for like an ideal gas, and you might have a gamma minus 1. Well, that doesn't work. So you just realize these formulas that usually where you see gamma are derived for ideal gas, and clearly incompressible fluids are not an ideal gas. But this is certainly an easy way to do it. So I like Panton's derivation there. Chapter 3 was already index notation, which I pulled in to the left. We already taught that, so I will absolutely stick to index notation for sure. I've been doing that for a while in the book club. Chapter 4 is kinematics. This is nice. I'm not going to cover it here. Go read through it. It's a nice derivation. A lot of times when we have sort of started with conservation of mass, conservation of momentum, conservation of energy, this is a more formal definition of kinematics and what is a control volume and those things. So it's worth a good read. It's a again, mathematicians, which Dr. Panton is one. They want to be a bit more rigorous in how they define things. So chapter 1 is a rigorous definition of a continuum. Here, kinematics is going to be then a rigorous definition of control volumes and things like that. We're then based on things. So it's a good read. And within the kinematics, I'll switch to green here. Sort of the Lagrangian versus Eulerian approach. And so it's sort of a, hey, if you have a particle and you're following it, that's one approach versus, again, kind of the control volume approach. And we will use this quite a bit. So a lot of times we will have, in addition of stream functions, which we've seen, at least in 2 dimensions, can be pretty easy. But a lot of times flow visualization, we'll actually get it into the graduate level here. What does flow visualization require? And so if you've ever seen pictures like smoke going over a car, or smoke going over a wind tunnel, we use that as flow visualization, and it's important from both this kinematic point of view, but also then kind of zooming in what's required for that actually to be considered visualization versus just a two-phase flow. And so that was really interesting. And then for sure there's the definition of the material derivative. And so we're going to see this a lot, and really that's just the time rate of change, and then plus, I'll just say uj del j of whatever you're doing. So that's the material derivative, and so it's going to have that sort of convective term in there, and so we'll simplify this a lot, and Panton goes through and sort of rederives that. So it's good. Okay. Such that chapter 5 is then just a review again of conservation of mass, momentum, and energy, and all of the fundamental equations that we've already done so far. So that's a good review. And then chapter 6 is then really where this lecture is kind of going to start with viscosity. And so what we've done so far is sort of blast through viscosity and just do a very basic set. And so now I'm going to come back and be a little bit more complete. Again, that's why I like Panton as a graduate book, and kind of a mathematician, let me be accurate. So really, if you look at the stress tensor, which we've already talked about, and this is it's a tau ij, the way you build this up is you say, okay, this could be anything. It could be based on some other matrix A, and then it could also include some, and this is why index notation, I, J, K, L, of some other matrix. Gosh, I can't even read my own writing. I'll just say C of K, L for a moment. Okay, so this is really the most generic form that you could do it. And so index notation, so there's an implied sum over K, implied sum over L. This is Einstein notation, so again, it's 1, 2, 3 for X, Y, Z directions. We're not summing over time. This is not a general relativity course. And so then from this, there are a couple key assumptions, and I'll write them in green. So sort of step our way through to where we land, where we sort of landed in the past already in kind of our discussions of fluid mechanics. So the first one is isotropic. And isotropic, okay? And what isotropic means is there's no preferred direction. And so if you're a piece of fluid and you're looking this direction, this direction, this direction, they're all the same. So it doesn't matter if this coordinate is rotated or not. the fluid is, it doesn't mean the fluid's the same in all directions. That would, there are derivatives, but it just means there's no preferred direction, okay? And so that's going to come back to help simplify this. The second one is that there's no moments, okay? And this is actually conservation of angular momentum. And so it's going to then result in a symmetric tensor. Okay? And so then, based on those two assumptions alone, and it does a good derivation there of the angular momentum. So go read it. I'm not going to do it here. It's more math for just effectively saying that the stress tensor is symmetric. Then you are left with tau ij is equal to, so I'll call constant some a1, different a, apologies, trying to stick to the Manhattan's notation, some coefficient a1 times del ij, that's just your identity matrix, plus some other constant, or coefficient a2, which is then related to the divergence of the velocity field, del k uk, times del ij, and then some a3, and I'll write it down here, a3, and then this is the symmetric derivative, right, which we've already talked about, okay, in some notations, okay, symmetric versus antisymmetric. So this is the form, okay, and then we sort of build up. We have already an idea of the mechanical pressure. So remember back, we drew sort of a Cartesian box, and we talked about stresses on this face and stresses on this face. We already kind of talked about this. And so the mechanical pressure here would be the ones on the main faces. So P mechanical, and usually we'll do it with a minus sign, is 1/3 tau I. Okay, so Einstein notation, this is the summation over i's. And so this is basically the sum of the diagonals and then divided by 3. And so this is the mechanical pressure. Okay, it's the portion that is sort of applied mechanically everywhere. All right. And so after you finish writing this, we can now say pressure minus mechanical pressure, and then there is a model. So it's lambda plus 2/3 mu of the divergence. So del k uk. Okay. But then if you then apply the definition by conservation of mass, even for a compressible flow, that is then equal to, so this term comes over, lambda plus 2/3 mu, and you have 1 over rho times the material derivative of rho. That's actually conservation of mass. All right, so this whole thing is called bulk viscosity. Bulk viscosity. This entire term. All right. And so then the next assumption is called Stokes' assumption, which is basically saying that it's basically saying that the thermodynamic pressure, ones we would associate with a thermodynamic state variable, back to our thermo, that's why I'm teaching this together, and mechanical pressure are the same. Okay, what does that force us to have happen? Well, that forces lambda to be equal to minus 2/3 mu. Right? That's what that Stokes assumption drives. Okay, and so then in the end, and I'm getting a little low, but I'll finish it. That means the stress tensor is minus pressure del ij, and pressure and mechanical pressure are the same thing. That's basically what this A1 coefficient is, just minus, because we usually treat pressure as a minus. Minus 2/3 mu, and then del k uk del ij. And so that would be true if you have a compressible flow. So if it's incompressible, this term wipes out. That's why we haven't played with it so far. And so this is true for compressible flows. And then 2 mu Sij. And here we've talked about the strain rate tension before. The factor of 2 is because in Panton's book he does define it as sort of twice, or 1/2. Sorry, I'll write that here. Sij is 1/2 of del del I uj plus del j ui. Just for consistency. Sometimes some authors keep it as twice, others basically get rid of this half and just push it together. So, okay, so that's the stress tensor, right? And so again, this is true for compressible flows, and you can see why this was not done in undergrad. Where in undergrad it was just easy to be like, no, you've got, undergrad basically stopped with this, and I'll redraw because we're going to talk about it, where you have a fixed wall and you have another wall. This top wall is being pulled at some velocity, capital V, and so your fluid flow is linear, and that's basically where we got to, and we knew that the stress on that, because if you're actually running this experiment, you could measure the stress, and it's related to that gradient, okay, and it's linear, and so actually viscosities a lot of times are basically measured by that. Usually it's a disk with a really thin annulus, and you're measuring the torque that you have to do to spin that velocity at a certain rotation rate. So you can back this out. But that gives you this. And so a lot of times you got to be careful. Right? People would say, oh, it doesn't necessarily give you all the viscosity, but it works pretty well for incompressible. And these assumptions are not bad. Okay. Again, there are other really weird problems that can show up again in rarefied gases over here. But there are also some really interesting fluids. Okay, and so one of the interesting fluids is you can have this range of effects that happen with viscosity. And so if you've ever seen like shear thickening, it's actually been going around the internet, some really cool videos. Like it's like this white fluid that you punch, and if you like punch it, your hand doesn't go through it. But if you slowly kind of drop your finger in, it works, right? So that's shear thickening. Shear thinning is would be quicksand, right, where you actually go into it, and it sort of, as shear shows up, it drops in. That's why it's pretty be a big trap, right? So you see it in the movies quite a bit. So I'm plotting here. This is shear stress, and this is strain rate. Usually, sort of strain defined by this the moving of the particles. So this line is Newtonian fluid, and what we mean by Newtonian is basically it's linear. Okay, so that's this formula down here, a Newtonian fluid. Okay. This would be an example of shear thinning, shear thin, which, again, quicksand. And then there's actually an interesting one up here that Panton shows. That's a Bingham plastic. This would be a thing that doesn't move at all until you have a certain amount of stress, and then it moves linearly. So there's some pretty weird materials out there. And a lot of this comes from, again, intermolecular mechanics and all these different pieces, like long strains of molecules. And so, while we may be okay with continuum, right, where it still might be considered a fluid, the underlying weird mechanics of actually molecularly what's going on can actually create some really interesting cases. Okay, and so then in sort of chapter 6 and chapter 7 in Panton, then he really kind of starts going into, and that's where I'll finish off. And so this is kind of quite a bit of reading if you're going from scratch. But again, this is most of this is review. And so to kind of finish off, what is nice in chapter 7, and this is why when getting into the graduate fluid side of things, you're going to see a bunch of these flows that we can actually go solve. And so one is sort of a gravity flow, where again here's a wall, and then I didn't draw that very straight, but it's basically fluid A and fluid B, and then this is just air, effectively like no stress. And so if you look at the velocity profile, I'll do this in green, then you can have sort of one function, and then you could have another function, because basically the boundary conditions here is that stress has got to be equal to 0, because it's effectively saying the air isn't providing, it's moving really slow. And then the boundary condition here is that the stresses are equal. And so if they have different viscosities, then you can actually solve for this double film, and it's on an inclined slope, and so the actually driving force is gravity. So you can go solve that. So go solve that. You go work through some of the problems. And then the last one that I'll just sort of highlight, and I'll let you do the math and go through it. I'll show you the similarity variable. But the last one is actually then a wall that is then starts impulsively tug to the right at speed v at time equals 0. And so what happens is that if this is, say, the fluid, what you're going to have is, as sort of a function of time, that the fluid is the velocity is going to increase, and you're going to start to see this go up. And so when you go solve this, this is basically only the x momentum, and so you have rho, but it's a time rate of change still shows up. The cross term doesn't show up, and then you have mu del squared u dy squared. And so this is pretty neat. And you kind of go through with the similarity variable, right? And then in the end, the similarity variable, so eta, you actually will write as y over 2 square root of kinematic viscosity and time. So I think it was maybe last lecture, the one before, we actually talked about the Blasius boundary layer, where you had, again, in this variable eta. And so the work is you basically go transform this equation using etas, and then you then define f to be the velocity over this sort of, I better call that, let's call that v naught, okay, over that initial tug. And it's a constant tug. As soon as you start tugging, you keep tugging. That's f. You'll then end up with a differential equation that is f double prime plus 2 eta f prime equals 0, which has a very easy solution. It's the error function. So 1 minus the error function of eta. And really the important one, if you haven't seen the error function before, is actually the derivative. The derivative is some constant that yet to be determined times the exponential of minus eta squared. And so it's a well-defined function. Usually you look it up in tables. So your mathematicians would have defined it, and you do a table lookup. Almost every single, whether you're doing like Python, MATLAB, any of those things are going to have error functions. I think even like Microsoft Excel has an error function. So it's a standard mathematical function, just like sine and cosine. It's just usually not one that you see of until you get to like this kind of stuff, right? So anyway, this is sort of the power, and this is we're gonna see this in the next couple of lectures. We can kind of keep going through and solving for these flows, where sort of the undergraduate level, this might be considered too much math. What it does for you, again, that reminder of my student that said, Andrew, I forget what's wrong with undergraduate mechanics. Undergraduate engineering is that they should have started with graduate school. Again, to not be bashfully ashamed about the math, you can kind of follow along in the books, and that because we've upped our math, it lets us actually get into real flows. And so this is where you're going to start developing an intuition for fluid flows, is because you've solved real things and you've done real things, and you start understanding. And that intuition then, what's going to happen around flows around airfoils, flows in gas turbines, all flows within rockets, all of that intuition starts coming because you've not been ashamed of the math or afraid of the math. You go in, you can actually solve these equations, and this ultimately should make sense. So that's the point of it. So that's kind of the intro of Panton. Again, we've been kind of teaching this and going through this all throughout the fluid mechanics, all sort of the advanced math and different pieces. And this is just a good summary with kind of finishing up the things that we can, starting to solve the things that we can, and that's sort of that graduate level. So we'll see you next time.